Total zero-divisor graph of a field. Abstract, let F be a field with Z, F, its set of zero divisors. The total zero-divisor graph of F, denoted Z, F, is the undirected, simple, graph with vertices Z. Asterisk equals Z, F, dash 0, the set of non-zero, zero divisors of F, and for distinct x, y. Asterisk the vertices x and y are adjacent if and only if x plus y dot z, f. In this paper, we study if z, f, is finite and every vertex of z, f, has a finite degree, then f is finite, and also prove that z, f, connected with diam equals 3. Introduction. In this paper, we study the total zero-divisor graph is the undirected graph with vertices z, f, asterisk equals z, f, dash 0. The set of non-zero zero-divisor of f and for distinct x, y, z, f, asterisk, the vertices x and y are adjacent if and only if x plus y dot z, f. It is denoted by z, g, f, and is the induced subgraph of total graph. We show that z, g, f, is finite, then f is finite and not an integral domain, if every vertex of z, g, f, has finite degree, then f is finite, and also prove that z, g, f, is connected with diam equals 3. For some other recent papers on zero-divisor graphs. 2 preliminaries. 2.1 Definition. The number of edges incident with a vertex v is called the degree of v, and it is denoted by d, v. The minimum and maximum degree of a vertex of a graph are respectively denoted by and. 2.2 Definition. A graph G in which every vertex is adjacent to every other vertex is called a complete graph. Complete graph is represented as where n is the number of vertices in. 2.3 Definition. The chromatic number of a zero-divisor graph of a ring R, denoted by G0, is the minimal number of colors required to assign each vertex in a zero-divisor graph a color so that no two adjacent vertices are assigned the same color. 2.4 Definition. A graph G0 is a k-colorable if G0 can be colored with less than or equal to k colors. 2.5 Definition. A graph G is said to be a connected graph if there is at least one path between every pair of vertices in G, otherwise G is said to be a disconnected graph. 2.6 Definition. Any two distinct vertices A and B in graph G, the distance between A and B, denoted by d, a, b, is the length of a shortest. 2.7 Definition. A ring R is called a coloring if G0 is finite. 2.8 Definition. An element x.R is said to be a zero-divisor if there exists some element 0y.R such that xy equals 0. 2.9 Presumption. G0 equals 1 if and only if R equals 0. 2.10 Presumption. G0 equals 2 if and only if R is an integral domain, RZ4 or R Z2 / 2. 2.11 Definition. The chromatic number of a zero-divisor graph of a ring R is equal to the clique number of the ring. That is, G0 equals CL, R. 3 Main result. 3.1 Theorem. Let F be field, then the total zero-divisor graph if finite if and only if either or an integral domain. In particular, if 1 equals Z, G, F, equals 8. Then F is finite. Proof. Let F be a field and Z, F, be the set of zero-divisors in F, and let Z, G, F, be the total zero-divisor graph. Then all vertices of Z, G, F, is non-zero, zero-divisor of F. It is trivial that if F is finite, then Z, G, F, is also finite. Suppose that Z, G, F, is finite and non-empty. This implies that Z, F, is finite. Suppose these are two elements U, V.F, U0 V0. Such that U plus V.Z, F, let I equals N, Z, then U plus V.I since U plus V. This implies that I Further, I is finite and f, u plus v, dot I for all f dot f dot u plus v f dot f dot f, u plus v, dot I. Suppose f is finite dot then there is an I dot I such that k equals f dot f slash f, u plus v, equals I is infinite. For any f, t dot k, f, u plus v, equals I, t, u plus v, equals I, ft, u plus v, equals 0, ft, dot n, u plus v, since, k dot n, u plus v, k is ft dot j dot ft van, u plus v, infinite, where k dot n, u plus v, since ftz, f, i.e.n, u plus v, dot z, f, is infinite, a contradiction, therefore f must be finite. 3.2 Theorem. Let f be a field with identity. Then S equals f times 0 2 is a field without identity, S equals z, s, and g, s, g, f. Path connecting A and B. Proof, clearly S equals z, s, and t has no identity. Define, f slash s slash by, u, equals, u, 0. It is easily verified that, u, equals, v, for u, v, f if and only if, u, 0, equals, v, 0, and, u, 0, equals, u, 1, for every u. F thus is a well-defined bijection. Moreover, restricts to a graph isomorphism from G, F, to G, S, since, U, 0, V, 0, equals, 0, 0, if and only if UV equals 0. 3.3 Theorem. Let F be a field such that Z, F, is not an ideal of F, then Z, F, is connected with diam Z, F, equals 2. Proof, each U asterisk is adjacent to 0. Thus, U0V is a path in Z, F, of length 2 between any two distinct U, V. Asterisk. Moreover, there are non-adjacent U, V. Asterisk since Z, F, is not an ideal of F. So, diam Z, F, equals 2. Hence proved. 3.4 Theorem, let F be a field then Z, F, is connected with diam equals 3. Proof. Let U, V be vertices in Z, F. There exists U plus Z dot Z, F, V plus W dot Z, F, if U plus V dot Z, F, then UV is a path of length is perpendicular containing U, V. If U plus VZ, F, and W plus Z dot Z, F, then U and V are contained by a path of length equals 3. If U plus V dot Z, F, and W plus ZZ, F, then U and V are connected by a path UV of length equals 2. Hence proved.